Welcome to the second session of the step response of RC and RL circuits. In the previous session we have discussed about the step response of RC circuits. In today's session we will be discussing about step response of RL circuits. We have finished problem number 4. Let us move to the problem number 5, in which we are going to evaluate the inductor current for both before switching operation and after switching operation. For problem number 5 we are having two circuits. If we check this circuit A, in which the switch is initially open before switching operation, and then after switching operation the switch is closed. After the switching the switch is closed. If you observe after the switching operation, when the switch is closed, the circuit which we need to consider is the part of the circuit which is having the inductor. Hence we will consider this part, and this part doesn't have any source. This RL circuit, it is a free response circuit, whereas this circuit after switching operation B part, even it does not have any source. Before switching operation it is connected to a voltage current source. After switching operation, when the switch is removed, it does not have any source. It is a free response. We can say that these two circuits are free response circuit. The RL circuit does not have any power supply. If we go into the solution, problem number 5, step response of RL circuit, these are the two circuits which we are using here. If we go for the first part, before t is equal to 0, this part of the circuit, it means this is not connected. Initially this part is not connected. Only this 3 ohm resistance, 2 ohm resistance and the inductor are connected. 3 ohms and 2 ohms, and inductor is short circuited. The current through the inductor is I. Before switching operation is 0. I of 0 is equal to, by Ohm's law, 25 by 5. 3 plus 2 is 5. You will get it as 5 amperes. After t is equal to 0, this circuit, after t is equal to 0, it is short circuited. It is short circuited means the current which is coming here is getting divided in this short circuit part, and some part is moving here. It is short circuited. We can say that the supply whatever is coming is flowing through this, and the stored energy which is coming, it is present here, will be flowing through this. It means this is separate part and this is separate part. We are no way concerned with this part. We are concerned with the current flowing in the inductor. Hence we will consider this part. After t is equal to 0, the circuit consists of only 4 ohms and 4 henries and 2 ohms. This part is considered 4 ohms and 2 ohms. Hence we will write it as, after t is equal to 0, it is a free response. It does not have any power supply. Hence the current flowing in an RL circuit without any external power supply, is I of t is equal to I naught e power t by tau. I naught value is L by R. For a RL circuit, L by R. So L value is 4 and R value is 2. You will get tau as 2, and I of t is equal to I naught e power minus t by tau. You will get it as I of t is equal to 5 e power minus 0.5 t. This is for free response. This circuit is free response circuit. Coming to the second circuit, before t is equal to 0, inductor acts as a short circuit. Before t is equal to 0, if you go into the circuit, at current which is flowing, initially it is connected. When it is connected, it is short circuited. When it is short circuited, whatever current is coming, the current flows through a low resistance path. It does not have any resistance. The resistance is 0. When the resistance is 0, whatever current is present here, it will flow through this. If you want to check with the current division also, you will get the same thing. Current division means these two are in parallel. We can change 4 into 2 divided by 4 by 2. You will get it as 8 by 6. 8 by 6, and the resistance here is 0. So the current flowing through this will be 4 by total current 6 into opposite resistance, whatever we are having this resistance, divided by the total resistance, whatever current is flowing, you will get this current value. It will be equal to this value, same current. So simply we can write it as I naught of 6 is equal to 6 amperes. It will be a short circuited. It will be a short circuited. I naught of 0 is equal to 6 amperes. Whatever current is present here will flow through this inductor. Next, at t is equal to 0, we got this current value before switching operation. After t is equal to 0, if you check this circuit, after t is equal to 0, it means when it is removing, when we are removing this, only this part is isolated and this part is isolated. We can say that it is an RL circuit without any power supply, hence it is an RL free response. As it is an RL free response, you can write it as I naught I of t is equal to I naught e power minus t by tau. What is tau? Tau is L by R. L by R is 3 by 2. L value is 3 and R value is 2. You can write it as 1.5. So I of t is equal to I naught e power minus t by tau. Tau is 1.5. I naught value is 6. This forms your free response circuit. Why we have explained this? Just to differentiate the forced response and free response circuit. These two circuits are free response. Let us go to the forced response circuit. Coming to the problem number 6, we are having, if we go to the problem number 6, the obtained the inductor current for both t less than 0, t greater than 0 in each of the following circuit. We are having one circuit here, we are having another circuit. To start with this circuit, A and B, they are represented here side by side. Coming to this first circuit, initially this part is open. Power supply is there, 4 ohms, and parallel to that we are having an 4 ohms and an inductor part. We need to identify the current before switching operation. Before switching operation, what is the current through the inductor? Current through this inductor will be, current is coming here and getting divided, some part of the current is getting divided here and in this branch. So I naught is equal to, by current division method, total current into opposite resistance 4. We want this current IL in the inductor. So the opposite inductor will be, opposite branch resistance will be 4 ohms divided by the total resistance 4 and 4. We are not considering this. Why? Because this is inductance value and it has resistance 0. The inductance is in henries. And what happens when current flow through this? This inductor will act as a short circuit. Only these two resistances are present in the circuit. Hence the current which is coming here getting divided in this 4 branch and this branch. You can write it as 2 into 4 opposite branch resistance divided by the total resistance 4 and 4. You will get it as 1 ampere. Next, coming to the after switching operation, after t is equal to 0, it means this switch is closed. At t is equal to 0, the switch is closed. Now you can observe these two are in parallel. To this, or we can say this branch, newly added branch, is parallel to the next two adjacent branches. So what we can do, we can combine these two branches which will be parallel to this branch. Why we are not combining with this? Why? Because we need to identify the current here. So we will replace 4 and 12 with a new branch combined with as they both are parallel across the same terminals. We will replace 4 and 12 with a parallel equivalent resistance, and then we will identify the current through this. Now if you want to calculate this current, I am replacing 4 and 12 with a single resistance. It will be 3 ohms, which is parallel to 4 ohms and 3.5 ohms. Now at this situation, the current flowing through this inductor, we call this current as an I infinity after switching operation. Which is equal to 2 into 3 divided by 3 plus 4. 2 into 3 divided by 3 plus 4. Why? By current division method, we want this current. This current is equal to total current into opposite resistance 3 ohms divided by 3 plus 4. and this this is not resistance value, this is henries, 3.5 henries, this is 3.5 henries, hence we will not consider this. Only resistance what we have in this branch is 4 ohms, hence we take 3 divided by 3 plus 4 is equal to 6 by 7. This forms your infinity. But what is the current, instantaneous current after switching operation? I of t is equal to I infinity plus I naught minus I infinity into e power minus t by tau. Tau is L by R. How to calculate L by R? L by R is equal to, only these two are present in LR circuit after switching operation. After switching operation, we for evaluation of these L and R values, L value is 3.5. Across this L, if we check the total resistance what we have, is 4 and 3. So 4 and 3 together you can write it as 7. Both are in series. 3 plus 4 you will get it as 7, and L by R tau value is equal to 1 by 2. Just substitute these values. Tau value here 6 by 7 I infinity, and I naught. I naught is 1. Just substitute the value, you will get I of t after switching operation. This is a forced response circuit. If we don't have this power supply, then I infinity will become 0. It is similar to that of a free response of the circuit. Coming to the second circuit, it seems to be a typical one, but it is easy one. This is the circuit. Initially this circuit is open. When this switch is open, we are having an voltage source in series with the 2 henries, 3 henries and 2 ohms. So the current flowing through this inductor will be equal to, it will be a short circuited, total voltage divided by the Ohm's law divided by the total resistance. I naught is equal to 10 divided by 2 plus 3 is equal to 2 amperes. We got the current before switching operation. After switching operation, after t is equal to 0, we can write it as, say this is the current I1, this is the current I2, and this is the total current entering at this branch. So we can write it as, sum of this current should be equal to this current by Kirchhoff's current law. So you can write it as 10 minus V divided by 2 I1 plus I2 is equal to I1 by is equal to total current I. I am writing the current in this branch as 10 minus V divided by, I am naming this voltage as V. So the current flowing here will be equal to, either you can write V minus 10 by 2, V minus 24 by 6 is equal to V minus 2 by V minus 0. The voltage at the other, we don't have any power supply here as we have, so we can write it as V minus 0 by 3. But this current is negative, but this current will be opposite to this, hence we can write it as 10 minus V by 2 plus 24 minus V by 6 is equal to V by 3. What should be the normal equation based on this current value? If the current flowing like this, it will be V minus 10. This should be the higher potential. So what we can write, 10 minus V by 2, or you are supposed to write V minus 10, V minus 24 divided by 6, and this should be V minus 3 by 2. But as the current direction is opposite here, this is positive, so I am writing 0 minus V by 3. As to remove this negative here, minus V by 3, to remove this negative, I have shifted that negative this side. So you can write it as 10 minus V by 2, 24 minus V by 6 is equal to V by 3. Now if you apply simplification method here, you can write it as, in the LCM you are having 2, 6. Here we are having 2 and 6, means the LCM will be 6. So 2, it will become 30 minus 3V, 2 into 3, it will become 6. It means 3 is the product. 3 into 10, 30, minus 3 into V, minus 3V, plus 6 is 1, the LCM is 6, 6 divided by 6 you will get it as 1, 1 into 24, 24, 1 into minus 4 is equal to, actually you are supposed to write it V, and this whole expression by 6, I am shifting this 6 this side, so you will get it as 6V by 3, 6V by 3 is equal to 2, 6V by 3 is equal to 2, hence I have written it as 2V. Together if you simplify this, we will get 54 minus 4V is equal to 2V, or 54 is equal to 6V, or V is equal to 9 volts, or simply you can write, but this is what, this is just the voltage, but what we want the current through the inductor. Current through the inductor I of t is equal to, we got it as V by 3. Hence I will write it as V by 3 is equal to 9 by 3 is equal to 3 amperes. This is what, this is the current, 9 by 3 is the current after switching operation. So I of t is equal to I infinity plus I naught minus I infinity e power minus t by tau. In this situation, what are we supposed to do? Substitute the value of I infinity that has been evaluated, and then substitute the value of the I naught which has been evaluated here, 2, and you will get tau value. Tau value will be across this inductor, you can see 3 is in series to the parallel combination of 2 and 6. 3 in parallel combination of 2 and 6. 3 plus 2 into 6 divided by 2 plus 6. You will get it as 4.5. 3 plus 2 into 6 divided by 2 plus 6. Hence you will get R equivalent as 4.5, or simply tau is equal to L by R. L value is 2, R value is 4.5. You will get it as 3 plus 2 minus 3 e power minus 9t by 4. 9t by 4. This forms your problem number 6. Coming to the last problem, we need to calculate the voltage across this inductor, or the same thing. Voltage across resistance means it is also equal to voltage across the inductor after switching operation for t greater than 0, and the initial current I of 0 is 0. The initial current in the inductor is 0. It means I of 0 is equal to 0. Now if you go to the solution, this is the circuit. 4u of t is the step input. 4u of t is the step input. It means I of infinity is equal to, final value is 4 times the unit value. 4 times the unit value is 4 into 1. You will get it as 4 amperes. It means 4 is the final value. 4 amperes is the final value. And the initial current, it has been specified as 0. It has been specified as 0. It means you can write it as I of 0 is equal to 0. R equivalent across this inductor, 5 ohms and 20 ohms are in parallel, and this will be open circuited. This is current source, hence it should be open circuited. 5 and 20 are parallel. We can write it as 5 into 20 divided by 5 plus 20. You will get it as 4 ohms. This forms your equivalent resistance across this inductor. Now tau will be what? Tau is L by R. L by R is equal to 8 by 4 is equal to 20. Why we have calculated this? We need to calculate the voltage. To calculate this voltage across the resistance, we need to calculate the voltage across the inductance. Why? Both are same. If you want to calculate the voltage across the inductance, for inductance, easy calculation is identifying the current through the inductance. Hence we will calculate the current first. Current through the inductance is equal to 4 1 e power minus t by tau. So it's not 4, it is, we can write it as I of t. Current through the inductor is I infinity plus I of 0 minus I infinity into e power minus t by tau. Tau has to be evaluated. Initial current is 0, it is given in the problem. I infinity has to be evaluated, it is given as 4. I naught, I infinity is given. I naught is 0, initial charge is 0. I infinity is 4, it is given. Tau value is L by R. L by R means across this L value is here, L value is 8, and across this we are having two resistance 5 and 20. Hence we got it as 5 into 20 divided by 5 plus 4, we got it as 4 ohms. Now substitute all the known values. I infinity is 4, 4 plus I naught is 0, 0 minus 4 into e power minus t by tau. Tau is 2, substitute 2. You will get I of t is equal to 4 into 1 minus e power minus t by tau. But this is not our final target. Our final target is to evaluate the voltage across the inductor. Voltage across the inductor is voltage across the resistance in this problem. If you check, we want this V. V is also equal to the voltage across the inductor. So voltage across the inductor is equal to L di by dt. Electrical circuits 1. In electrical circuits 1, when we are working with AC circuits, we got this L di by dt. So in place of I, we will be placing this 8 into d by d dt, 4 into 1 minus e power minus t by tau. In this, substitute the value of differentiate this equation. If you differentiate, L value is here 8, d by d theta of 4 into dA by dt. In place of I, we are replacing this 4 into 1 minus e power minus t by tau. T by tau is t by 2. So you can write it as LdA, you can write it as 8 into d by ddt of 4 into 1 minus e power minus t by tau, 8 into 4 into 0 minus e power minus t by tau into minus 1 by 2. When you differentiate this, differentiation of 1 is constant 0 minus differentiation of this is e power minus t by tau into minus 1 by 2, minus minus cancel, you will get it as plus. You will get it as plus, and here you are having 8 into 4, 32, 32 divided by 2, you will get it as 16. So you will get it as 16 e power minus t by tau. With this we have finished problem number 7. We have in this chapter, in chapter 2, we have studied problems related to the step response of RL circuit, step response of RC circuit, and also for easy understanding, for the comparison with the force response or step response, we have evaluated the problems related to the free response of RL circuit also. With this I conclude. If you are having any doubts, you can discuss it. Thank you.